This is my spreadsheet program. It is written in the language Gforth. Gforth is a general-purpose programming language that lets you steer clear of the large commercial operating systems. You can even avoid the open-source Unix-like operating systems like Linux. Not only is my spreadsheet program written in Gforth, but you write your spreadsheet cell formulas in Gforth. Let me show you how it works. A spreadsheet has cells. You can enter a number into a cell, or you can enter a formula. A formula produces a number by computation, often using numbers in other cells. My program requires an implementation of the Gforth language called Gforth. Gforth runs my spreadsheet program, and Gforth interprets your cell formulas. I have defined special words you can use in your formulas to fetch the values of cells elsewhere in your spreadsheet. But otherwise, you use plain Gforth in your cell formulas. No restrictions. Use any Gforth words you like. Before we look at some spreadsheet examples, let's see how Gforth handles numbers. Gforth is a simple programming language. In a Gforth system, there's a working area for data called the stack. A stack is a list that you alter by adding and removing elements at the end. In Gforth, you enter operands followed by operators in a style called postfix notation, or reverse Polish notation, as in some calculators, like the HP12C financial calculator. How many minutes are there between 9 a.m. and 1 p.m.? Here's a Gforth expression that answers the question. 13 space 9 space minus space 60 space star space dot. 13 because 1 p.m. is 13 hours after midnight, and when the interpreter reads 13, it puts the number 13 on the stack. The interpreter reads 9 and it puts 9 on the stack. Then the interpreter sees minus, which it recognizes to be an operation. So it executes that operation, which is to replace the last two entries on the stack by their difference, 4. The interpreter sees 60 on the input stream and puts the number 60 on the stack. Then it sees star, which stands for multiplication, so it replaces the last two entries on the stack by their product, 240. The dot removes the last entry from the stack and prints it as output. 1 p.m. is 240 minutes after 9 a.m. Now the interpreter has finished reading the input stream and it prints OK to output. Modern computers deal with not only integers, as we have just seen, but also floating point numbers like -0.009. You might write this as -9 times 10 to the -3, called scientific notation when I was in school. And Gforth has a similar notation, -9e -3. You cannot use the notation -0.009 for this floating point number. It's not an error, it's just that this notation with a dot but no e has another meaning in Gforth. Gforth has a separate stack for floating point numbers and separate operators like f star and f dot. So for example, if you enter 314159e minus 5, that's roughly pi, followed by 2e, then you'll have pi and 2 on the floating point stack. Then f star replaces them by their product, and f dot shows you the result, 6.28318. There's a lot more to Gforth, including the capability to define your own operators, or words as they're called in the Gforth tradition. Check out the book Starting Gforth by Leo Brody. You can find it for free online. Now let's look at some spreadsheets. This is my Foodstuffs example spreadsheet. You can see in the first column here green beans, anchovies, and butter. Each cell in the spreadsheet is associated with a Gforth program or a script. The cell scripts or numbers otherwise cannot currently be edited from within the spreadsheet application. Instead, you need to use a text editor. I use VI, so let's take a look at the cell scripts for the Foodstuffs spreadsheet. The cells, by the way, are indexed in the way that elements of matrices are in mathematics. First by the row and then by the column. Except in mathematics, the the row indices go 1, 2, 3, and so on, numbered from 1. Here they're indexed from 0, same for the columns. So the cell in the very upper left of the spreadsheet is 0, 0. So the word item there is in cell 0, 0, the word count is in cell 0, 1, and so on. So let's go row by row through the scripts that define these cells. Cell 0, 0 contains the string item. That's a Gforth notation for string. And following that is a statement that sets the background color. You can see it's a reddish color, kind of a pale reddish color. The values for the red, green, and blue are 220, 110, and 110. Each of these values is an integer from 0 to 255. The triple 000 defines a black color, and 255, 255, 255 is white. So this is a fairly pale cell with an emphasis on red. Alright. Next is cell 01. It contains the string count, and it has a pale greenish color, 110, 220, 110. Cell 02 contains the string unit price and a pale bluish color. Cell 03 contains the string cost, and it's a pale yellow. Cell 10 contains the string green beans. Let's see, cell 11 contains the number 4. And by the way, I mean, this is a complete Gforth program. It just puts the integer 4 on the data stack. That indicates to my spreadsheet program that this is an integer valued cell. So that's all there is to it. Let's see, what's in cell 12? That's the unit price of green beans. And you could express prices as integers, as whole numbers of cents, or as floats, and I chose to do floats. So 69 e minus 2, that's 69 hundredths. The units are dollars by my convention here. And there's a special statement here that sets the value sheet.formatD to the integer value 2. Gforth has a way of formatting floating point numbers by these 3 parameters, R, D, and P. You could read the Gforth documentation for details on that, but I believe I set format D to 2 so that I would have 2 figures to the right of the decimal point in the output of this column. All right, cell 13, that's the cost of green beans, and this is obtained from the previous 2 columns. We just multiply the count by the unit price. So 1, 1, RC to N. RC to N is my word to take a row and column index and fetch the integer that's there. In this case, that's 4. So after this RC to N, there's 4 on the data stack. And then N to F, that's my word to convert an integer to a float. So that puts 4e on the floating point stack. And then we get the unit price by 1, 2, RC to F. That fetches the float that's in cell 1, 2, puts that on the floating point stack. And then we multiply those 2 floats and leave the result on the floating point stack to indicate to the spreadsheet program that this is a floating valued cell. And we format that one also so there are 2 figures passed to the right of the decimal place. All right. On to cell 20, contains the string anchovies. The count is 1. The unit price is $1.99. And the cost is obtained by multiplying the values in the previous two columns, just as before. Row 3, we have cell 30, that's butter. Cell 31 contains the count 2. Cell 32 contains the unit price, $2.99, and the cost is computed in the same way as before. Cell 52 contains the string subtotal, and it's got a cyanish colored background there. The subtotal is computed by adding up the costs in that column in 3 rows above. So we fetch the value of cell 1.3, the value of cell 2.3, and the value of cell 3.3, and we add those together, leaving the total on the floating point stack. There's a 9.75% tax with a light gray background. The tax we of course want to compute automatically too, so that's 0.0975 times the subtotal, and then the total is obtained by adding the tax and the subtotal. Alright, and that's it for this spreadsheet. I did want to show this feature of spreadsheets, that when you change the cell contents, then any dependent cells are recomputed accordingly. So let's say the number of anchovies here, these are maybe little cans of anchovies, maybe the count rises from 1 to 10, let's say. So let's see, we want to change that value. Where's the count in cell 2.1? Right, so let's change it from 1 to 10. And what happens? Well, we look at the spreadsheet and nothing changed. That's because there's no direct mechanism for the text editor to notify the spreadsheet program that the cell has changed. But I can bump the spreadsheet here. By bump, I just mean I clicked the right arrow and the left arrow. The only controls in the spreadsheet are that you can scroll around. You can scroll to the right and left and down and up. If you just bump the spreadsheet by scrolling one column right and then one column left again, the changed cell being within the current display gets detected by the program. So you can see that the count changed from 1 to 10 in cell 2.1 there, and accordingly the cost rose from $1.99 to $19.90, and the subtotal rose to $28.64. The tax rose as well, and the total computed from that rose as well. So changes made to cells in the spreadsheet are propagated around the spreadsheet anywhere cells depend on that value. And that's it for the Foodstuffs example. My next example is called Rainbow, for no good reason. In the previous example, each cell had its own script, but maybe you want to be a little more programmatic about how the contents of the cells are determined. So this rainbow example has just 2 scripts, and neither one of them is associated to a cell. The first one there, called RC, is a script that gets evaluated when there is no script for the given cell. And this other file, head.fs, is a script that's read when the spreadsheet program starts up, and it's a good place to put definitions of words. So let's take a look at those 2 Gforth programs. The default cell script, rc.fs, just calls this word rainbow, which has been defined in the head. So let's take a look at head.fs, and you see this is the Gforth notation for the beginning of a definition. the colon signifies that the next word, rainbow here, is a word that's being defined in terms of previously defined words. Sheet.r and sheet.c are the indices of the current row and column, and these curly braces are Gforth's notation for local variables. So sheet.r and sheet.c are going to be referred to as r and c for the rest of this function definition, this word definition. And this is a conditional statement. If the column index is less than 4, then we do this. Otherwise, we do this. So in the first block, that is where the column index is less than 4, we take the row and column indices, add them, and compute the remainder when divided by 2. So that's 0 for even or 1 for odd. And then whatever that value is, we multiply by 255. So the value is either 0 or 255, and then twice we duplicate that. So, and set the background color. So we're setting the background color to black or to white. Black when the row plus column index is even, white when odd. And so you can see in the first 4 columns that indeed you get that checkerboard coloration. In the remaining columns, and by the way, that extends past what's visible here. What is the formula? So I took 3 numbers, 255, 0, 0, so that's red, and depending on which row we're in, we might move those numbers around. So R3 mod, that divides the row by 3 and keeps the remainder. And then this is a loop that runs the number of times equal to whatever the value of R3 mod was. And what do we do? Minus rot, that rotates these 3 entries at the end of the stack. I guess sort of to the right, with the rightmost element wrapping back around to the left. So and sets the background color accordingly. So depending on the row, the color is either going to be pure red or pure green or pure blue. You can see them alternating red, green, blue, red, green, blue in the image there. And that's it for the rainbow example. This is my binomial coefficients example. Binomial coefficients count sets of a certain type. We're talking about finite sets. A set that has n elements is called an n set. For example, A, B, C, D is a 4 set. And you could ask how many subsets of this 4 set there are, and it's well known that there are 2 to the 4 or 16, essentially because if you want to enumerate all the subsets, you have 4 binary decisions to make independently, and that is to whether to include A, whether to include B, whether to include C, and whether to include D. You could also classify those subsets by their size. There's one subset of a 4 set of size 0. That is, there's one 0 subset of a 4 set. That's the empty set. That count of 1 is reflected in cell 40 here. How many 1 subsets of a 4 set are there? There are 4, A, B, C, D. I think we just tallied that a moment ago. How many 2 subsets of a 4 set are there? There are 6. That's AB, AC, AD, BC, BD, and CD. how many 3 subsets of a 4 set are there? ABC, ABD, ACD, and BCD. And how many 4 subsets of a 4 set are there? 1, that's ABCD. So grouped together by size, you see all those counts, 1, 4, 6, 4, 1 in row 4 there. And the sum of those numbers is 11, 15, 16, which is equal to 2 to the 4 as we expected. So you could obtain these numbers by enumerating subsets in the way we just did, or you could be a little more clever about it. There's a well-known recursive formula. For instance, if we wanted to obtain the entry in cell 5-2 here, which you see is 10, let's say we didn't know the value. And we want to know how many 2 subsets of a 5 set there are. Let's say the 5 set is A, B, C, D, E. Some of those 2 subsets have E as a member and some don't. Those that don't are precisely the ones that were counted in the cell above. That's the 2 subsets of the 4 set A, B, C, D. So there are 6 2 subsets of a 5 set that do not contain the greatest element E. How many are there that do contain E? Well, all those that contain E as a member, you could just strip E away from those subsets and be left with a smaller set, a set smaller by 1, consisting of the elements, elements from the set A, B, C, D. So in the cell above and to the left, that is cell 4-1, you see that there are 4 1 subsets of a 4 set. So you add those together, 4 plus 6 is 10, and you can see in this table, every entry is the sum of the 2 cells, one directly above and one above and to the left. 15 plus 20 is 35, 21 plus 35 is 56, and so on. Provided that those 2 cells exist in the row above. And otherwise, it's quite easy to obtain the value. I mean, if the column is not between 0 and the number, 0 and the row index inclusive, then the number is 0. We don't even bother to list all the zeros. And how many, let's look at the first column. You see there are all 1s there. Of course, the empty set is the sole 0 subset of every set. And similarly, the diagonal here, where R and C are equal, how many R subsets of an R set are there? Well, there's just 1, the set itself. So if you fill in 1s along the diagonal and 1s in the first column, and then busy yourself about filling in the rest of the table between those 2 lines, then you'll see that every cell, if we go from top to bottom, every cell is populated in the cell above it and the cell above it to the left. So 2 is 1 plus 1, 3 is 1 plus 2, 3 is 2 plus 1, 4 is 1 plus 3, 3 plus 3 is 6, 3 plus 1 is 4, and so on. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, and so on. When you construct the spreadsheet, it's convenient to use that recursive formula. Before we look at the recursive formula, let's just poke around in this directory for a second. Now you see, again, there's a script called head and a script called rc. And by the way, the file name extension there of fs is Gforth's file name extension for Forth source files. But there's a directory there called db. The program is designed to record the output of the cell formulas, that is, to record the cell values, as well as the dependencies among the cells according to their formulas. And that's all stored in this db directory. So your important data is in a directory unto itself. Then inside that directory, there's this DB directory. The DB data is all derived from your spreadsheet data. So you want to keep your spreadsheet formulas in the form of these Gforth programs, but you could remove all the files inside the database directory, and they would be automatically recomputed by the program. So that could be useful in case your program really misbehaves. It should not be necessary to do that if the program crashes. And the whole point of writing these files to disk is that they'll persist even if the program crashes. Alright, well, so let's look at these files. There's, again, no individual cell script, but there is this default script, RC, and it just calls binom, which, as in the previous example, is defined in head. So again, we have the row and the column of the current cell, and we will call those R and C. And actually, it's important to obtain these values and store them in local variables, because R and C, these sheet.R and sheet.C, these are global values, and the way the spreadsheet cells are evaluated, some cells on which the current cell depends may need to be computed before we finish computing the current cell, and that would change the values of sheet.R and sheet.C. So we actually need to capture those values, the values of sheet.R and sheet.C, in these local variables R and C before any values are fetched from other cells. And so here we see that if the column index is no greater than the row index, then we're going to proceed. Otherwise, the cell is empty. Okay, so if the column index is 0, or that's the first column, by the way, or if the column and row index are equal, that's the main diagonal, then the value is 1. Otherwise, we're going to look in the row above and the column to the left and fetch that cell value. And we're going to look in the row above and same column and fetch that cell value and add those two together. That's the recursive formula. And that'll be the value of the cell. So there you have it. Here's a spreadsheet that computes the square root of a number by the method of bisection or binary search. You can see in the spreadsheet here the number 2 in cell 00. And bisection proceeds by keeping the square root of the input number inside an interval, and in each step of the algorithm splits that interval in half. One of the halves must contain the square root, and so you sort of keep that half and just repeatedly split the interval in half, keeping either the lesser half or the greater half, whichever one contains the square root. And in that way, the interval shrinks exponentially, reasonably fast, and you can see in roughly 10 steps that the square root of 2 is isolated to around 1.414 or 1.415. So how is that obtained in a formula? Let's look at the directory here. We have cell 00 contains the input number. We just chose 2. We can try some other values there in a second, but let's stick with 2 for now. So floating point 2. Row 1 is special in that it contains the initial interval. Let's see, 1 0, cell 1 0 fetches 0 0 RCF. That's the input number, in this case 2, and computes the minimum of that and 1. In this case 1 is the lesser of the 2. So you see a 1 in cell 10 there, and in cell 11 we've got, we again take the number whose square root we're looking for and 1, and we take the greater of those two and put that in cell 1. So there you have it. Those are the first 3 cells, and then the rest of the cells are obtained programmatically. So let's look at what remains. Again, we've got this RC, just refers to square root, which is defined in head.fs. So you see the definition there. Again, we get the row and column numbers and save those as RC. We're only using the first 2 columns here, so, and by the way, the first 2 rows are already dealt with in other cells, so this script only deals with the case that the row number is greater than 1 and the column number is 0 or 1. And in that case, we'll need the input number, and that's in cell 00. We'll call that x. This local variable with an F colon before the variable name is in Gforth a floating point variable. So x is a float. It's the entry in cell 00. We'll get the entry in the row above in column 0 and fetch that and call it x0. And we'll also get the entry in the same row but in column 1. We fetch that and call it x1. So x0 is the left endpoint of the working interval, the current interval, and x1 is the right endpoint of that interval. And we're going to split that interval in 2. That means we want to know the midpoint of x0 and x1. So here you have the sum of x0 and x1 divided by 2. So that's the mean. We'll call that xm. And now for the value of the given cell, we have a choice to make. I mean, we have to choose the left half of the interval if that's the half that contains the square root, and otherwise choose the right half. If the midpoint times itself is less than x, then the square root of x lies in the right half of the interval from the row above, otherwise the left half. So in case we're choosing the right half, then column 0 gets the midpoint and column 1 gets the right endpoint. Otherwise, the new left endpoint is the old left endpoint and the new right endpoint is the midpoint. You can look at as many rows of this as you like by scrolling down. Currently I have set the output precision so that no further digits are available, but you could tweak that and get better approximations to the square root of 2. So I said a moment ago we would try this out on some other numbers. Let's do that right now. So all we need to do is change the input value. We could change it to 20 and bump. Okay, looks like the square root of 20 is around 4.48. Sounds plausible. What about a number less than 1? Can we take its square root in the same way? Let's try 0.2. That is 2 times 2e minus 1. That's 2 times 10 to the minus 1. Oops. I need to save that, and we'll bump the spreadsheet, and it looks like the square root of 0.2 is around 0.447. Sounds about right. All right. This is my example Fizzbuzz. Fizzbuzz is a game and sometimes a programming exercise where you simply start counting from 1, 2, 3, 4, 5. Except when the number is a multiple of 3, instead of saying the number, you say fizz. And if the number is a multiple of 5, instead of saying the number, you say buzz. If the number happens to be a multiple of both 3 and 5, then you would say Fizzbuzz. So those are the rules, and let's see if we can do this in a spreadsheet. Well, of course I've already done that. Again, I have just two Gforth scripts here, RC and head. RC just refers to a function defined in head, and actually I defined two functions in head there. There's Fizzbuzz, the one called by RC, and there's a little auxiliary function append. Gforth can deal with strings, but it doesn't have a lot of words for dealing with strings. So I wrote this word append for the case where we have an address containing some text. Actually, this address is at the end of the working text, and you'll have some string you would like to append onto that. Strings in Gforth are often represented as a pair of numbers, first an address, then a count of how many bytes after that address should be included in this string. And so the idea here is we'll append this string adder1 u1 onto the original string, and we'll update the address by adding to the original address the number of bytes that were just appended. And by the way, I mentioned already that my spreadsheet cell values can be integers or they can be floating point numbers, and we've seen cases where they've been strings. So these are the three cell types: integer, float, or string. But in the previous examples, the strings have been simply labels, that is, constants. Where in this example, we're trying to produce strings that are dynamic. So here's the output. We're going to put all the output in the first column. So our program only proceeds if we're in the first column, and the game starts with 1. So let's just keep things lined up by skipping the first cell 0, 0. So in case the cell is positive, then we'll proceed. And so in case the number is neither a multiple of 3 nor a multiple of 5, we'll just put out the row number. And that, by the way, is an integer. We don't need to convert that to a string. The types of the cell contents are dynamic. We can just leave whatever is appropriate on the correct stack. So we've handled the case where the row index is neither a multiple of 3 nor a multiple of 5. Otherwise, we're not going to print the row number, but instead we're going to write fizz or buzz, possibly both. We'll start with S. S was defined up here to be sheet.string. That's a buffer, that's a working area that the spreadsheet program has set aside for the use of the cell scripts. So it starts off empty, and if the row index is a multiple of 3, then we append fizz to that buffer. And if the row number is a multiple of 5, we append buzz. And at the end, we need to produce a fourth string. That means a pair, an address and a number of bytes. And we've been keeping the address of the end of the string. We want to provide the address of the beginning of the string, so we push S and execute minus. So that computes the number of bytes that have been written in this block. And then we put S, that's the original beginning, and swap the two, so we get them into the proper order, the address of the beginning and then the number of bytes. And this is a string. So that's all there is to it. Did it work correctly? Let's see. 1, 2, fizz, 4, buzz, Fizz, because 6 is a multiple of 3, 7, 8, Fizz, Buzz, 11, we need to scroll down here, 12 is Fizz, 13, 14, 15, that's the first multiple of both 3 and 5. It says Fizzbuzz, and that's what's expected in this game. So let's see, let's check, does Fizzbuzz occur again at 30? It does. Okay, so this looks correct. My spreadsheet program runs on Gforth, and Gforth uses tools from the C world. Gforth runs on various operating systems. I would like for my program not to require an operating system, but for now, my program needs Gforth, Linux, and the X window system. I saw a presentation by Brad Nelson to the Silicon Valley 4th Interest Group of his Eclipse program. I don't know if you would call it an Eclipse calendar or an Eclipse atlas. His program downloads astronomical data from NASA and shows on a world map where eclipses have occurred and where they will occur. There are many neat things about this program, but for me the important part was the graphical user interface. Brad was using Gforth and its foreign function interface to call functions from the X window system, that is, Xlib. So I picked up the Xlib manual and the paper on the Gforth foreign function interface. Brad's source code is available online. I don't know whether he allows others to use his Xlib code, but in any case, I wanted my own implementation. And it was a pain, mostly because Xlib is complicated. This is just the sort of thing I'm trying to avoid when I use Forth. All I want is to set pixel values on the screen and receive input from the keyboard and mouse. Anyway, after a lot of reading and a fair amount of trial and error, I got it working. I could set pixel values on the screen and receive input from the keyboard and mouse. I did not want to deal with Xlib longer than necessary, so I wrote a glyph editor and I designed my own font. The glyphs are made of quadratic splines in such a way that each glyph can be represented by a 4-column matrix, and it's an easy matter of arithmetic to enlarge glyphs, shrink them, reverse them, shear them for an italic effect, and so on. This is how PostScript works, but PostScript uses cubic splines, not quadratic splines, for its fonts. I wrote a small numerical library for doing this matrix arithmetic in Forth. It is primitive and slow, but good enough for the purpose. I had developed a similar library for my volume estimation project. I implemented a hash table to store cell values, and I implemented data structures and algorithms to manipulate the graph of intercell dependencies. But I was losing data whenever I killed the program, so I wrote a little database management system and expanded it to store graph data too. With this design, my program should be able to accommodate very large spreadsheets. Here's a list of the software components I wrote, and the number of lines in each file. That includes whitespace and comments. 12 lines in this clock.fs. That's some performance measurement code. Memcheck.sh, that's a little awk program to help diagnose problems with dynamically allocated memory. The matrix arithmetic is 254 lines. Let's look at that. This is my matrix library. I have some conversions to and from, integer and float. Here's the matrix constructor. So a matrix is just consists of its dimensions followed by a pointer to a contiguous region of memory for the matrix contents, the entries of the matrix, which are floating point numbers, and then words for getting the dimensions of the matrix, so words for getting and setting entries of the matrix. There's a word to construct a matrix with constant entries, the zero matrix, the one matrix, the identity matrix, Here's a fold operation on the rows, a fold on the columns, words for putting the entries of a matrix to the stack and constructing a matrix from the stack. That might actually be useful for some small matrices. Words for gluing two matrices into a new matrix. Let's see. These are words to get matrices from a file, and elsewhere there are some words to send a matrix to a file. Memory zone. When you're working with matrices, you might have a long string of computations that you want to do. I used the end of the Gforth dictionary to do all this computation, because that in Gforth that's just sort of the natural place where some memory is available. So you could just do a whole long string of computations, constructing along the way all these temporary, results, these temporary matrices, and then at the end you could recover all that memory just by resetting the dictionary pointer to the value before all those temporary computations. Some routines for showing matrices. Here's matrix multiplication, transpose, erow. Let's see, I think that erow and e-column, these are constructing matrices of a single row or a single column that are all zeros except for a 1 in some place. Let's see here. Then there are these sort of pointwise operations, like matrix addition is done by adding the entries pointwise. Subtraction, similarly, the Hadamard product is done by multiplying pointwise. Max and min. So these are all done by a more abstract word called abin. Let's see, I have scalar multiplication, summing over the rows and summing over the columns, defined in terms of these folds that I defined above. The 2 norm, max over the rows, max over the columns, and so on. Diag, I think this is to make a diagonal matrix from a column matrix or a row matrix. I forget. Cross product, row normalize, column normalize. Matrix sort, so you can sort the rows of a matrix in this way. I think I used quicksort. My Xlib library and a lot of routines that aren't directly related to Xlib that have to do with drawing lines and rectangles, just various geometric primitives. 3,228 lines. That also includes, not just code, but data, I guess you would say. I mean, 2,300 lines of this are the font that I wrote, which consists of 1,900 quadratic splines. Let's look at that. This is my Xlib library. Let's see what we have here. We need to include certain headers. And define Gforth wrappers for certain C functions. So I'm using just a subset of Xlib, whatever functions I needed to get going. Let's see, apparently I made a wrapper from malloc. I forget if I actually used that anywhere. M time, let's see, is that the modification time? Some global values associated with the X session, I guess you might call it. Packing and unpacking of pixel data into integers. Test separate pixels, so some test code in there. Whiteout, blackout, applies to the whole screen. Xlib setup, so this is what you would call to populate the values of those session variables or session values when you start a program that is meant to write to the screen and receive events from the keyboard and mouse. Here's some numerical routines I wrote because I'm dealing with lines and splines below. So let's see, control points to coefficients, values to spline coefficients, and so on. Some more test code. Number of crossings, an array and a spline. This is a well-known algorithm for filling a loop, in this case a loop of splines. Let's see, stroke, touch up, point, seg, I forget what that is. Oh. That's a point on a segment. Does it lie between the endpoints or is it on the line outside? Let's see, pixel line, stroke line. Look, this definition is absurdly long by Gforth standards. Clearly I have some work to do on this file. Stroke glyph, place glyph, stroke glyph plus points. I think this is when I wanted to show the control points associated with the splines, the constituent splines. Fill glyph RC, again absurdly long by Gforth standards. Image data, yeah. So here I had to manage a buffer for all the video data. And let's see, at some point I get to the definitions of all the glyphs. My glyph program produces this output. And I just paste it into my Xlib file. Really should put that in a separate file, but let's see, upper B, upper C. This is the uppercase letter C. And so this is a matrix constructor. These 4 columns, these are the control points. The first column is X, second column is Y, third column is X, fourth column is Y. Each quadratic spline consists of 2 endpoints and a midpoint. The splines that make up my glyphs are arranged in loops. So a single spline consists of an endpoint, followed by a midpoint, followed by the next endpoint. And you might notice, depending on the glyph, let's see, J, K, L, M, it'll be a while before we get a glyph with more than one loop associated with it, but O, here's uppercase O, consists of an outer loop and an inner loop. You can see there's a separator, these minus infinities there. 394 lines in the glyph program. That's the program that you use to edit the glyphs in the font. 222 lines for a hash table, 149 lines in my digraph routines, 141 lines in the database management code. Let's look at that. This is my database management code. It just consists of a table where the records are of uniform size indexed by some primary key so you can quickly find the rows that you're interested in by their keys. It's a very simple system. There are no, you can't find, for instance, ranges of keys. So maybe instead of a database management system, you might call this a key value store. But let's see, seek byte. This is to find a particular byte of a file using file random access. Some code for fetching and storing integers and floating point numbers inside the table. Create database, destroy database, open and close, show the database contents. See, build an index, insert something into an index, shrink and expand the index. I mean, the index is essentially a hash table here. Either find or store a record. 239 lines that extend the database to deal with graphs. Let's look at that. This is my graph database management software. Of course, it uses my database management software or library. You can create and destroy a graph database, routines to show them, open and close the graph database. Here's some queries. Is a certain vertex present? Here's a word to add a vertex to a graph. Find, add, and remove. Let's see, these are set functions. I think I used my hash table implementation. There are routines for querying whether a certain arc exists in the graph. Routines for adding an arc to the graph. Words for removing an arc from the graph. Here's a word that removes all the arcs out of a given vertex from the graph. And by the way, the kind of graph I'm talking about is a directed graph. I'm keeping both a directed graph and its inverse, and that's so when you go to look up the neighborhood of a vertex, you can quickly find both its out neighbors and its in neighbors. You can adapt that as you like to a simple undirected graph. Let's see, remove vertex, so that'll do the sort of graphical operation of removing a vertex. That is to say, you not only delete the vertex from the graph, but all the edges that are incident to it, or all the arcs. Let's see. I have a word to do a search and return all the vertices that you can reach from a given vertex by arcs in the graph, directed arcs in the graph. So this is let's see, I forget if it's a depth first or a breadth first search. It's so simple, it's got to be one of the two. But and as the output, I return not just a set of vertices that you can reach, but a graph induced by those vertices in the current graph. And 824 lines to implement the spreadsheet. That's still a work in progress, and it could get smaller with some more work. And this does not include code I wrote that tests these various components. I would like to release the source code, but the spreadsheet code especially is, it needs more work. It's just not yet ready. Some features are missing from my spreadsheet program. Manual would be very nice. I'd really like to make a detailed manual to the level of showing what's going on in the source code. A cell editor to let you edit the cell scripts from within the application. Not only would this be convenient for the user, but it would simplify the communication from the editor to the spreadsheet program in as much as that's needed to decide which cells need to be refreshed when a script is altered. There are many features of spreadsheet programs missing from mine. I'm thinking of, elaborate number formatting options, maybe involving currencies or dates. Many spreadsheet programs give you a variety of fonts to choose from. I have only one font so far. Maybe spell checking menus and dialog boxes. These could be useful for organizing the many features, if ever there are many features. I actually kind of like the simplicity of the program right now without them, but who knows what the future holds. And online help. The background color of the cells is user configurable, but the color of the glyphs is within the cells is fixed to be black right now. I think that's actually really easy to change. I just haven't done it yet. It would be nice to be able to resize the columns independently of one another and the rows independently of one another from within the application. Currently you can resize them before you start up the application, but there's no dragging of column boundaries. It would also be nice to change the window size dynamically. Again, you can do this before you start up the application, but not while it's open. Currently, the program does not allow circular dependencies among cells. Actually, in some spreadsheet programs, you can have circular dependencies, and I guess this is considered a feature, although I don't know if it's very popular. There are many ways to work around this in the current program. If indeed nobody really cares for cycles, then I could make the spreadsheet program detect circular dependencies and reveal them to the user. But my thinking was it's actually pretty easy for the user to avoid circular dependencies. You can just adopt one of several kind of obvious rules. For instance, if a cell uses the value of another cell, then the used cell should be in a column strictly to the left of the using cell, or if it's in the same column, it should be strictly above. And finally, I want to talk about some issues that I ran into with Gforth along the way. If you go to the official Gforth page under the GNU project, they list version 0.7.3 as their current release, and I think this is kind of old. I think it's years old. I ran into trouble with local variables, which I use extensively in my code. There are some resource limits pertaining to local variables. For one thing, there's a local variables stack, and you could run out of space on the local stack as your program is running. The problem I ran into was not that. In my case, you could increase the size of the local stack when you start the program, and no matter how big you make it, I would still run into problems. My program would crash. It would crash trying to move something from the data stack onto the local stack, and I could never really get to the bottom of this. Second, I had trouble with exceptions. When an exception is thrown, there's supposed to be an exception code left on the stack, on the data stack, and in my case, there were times where more than one copy of the error code appeared on the stack, and I don't know if this had to do with some nesting of exceptions or what was going wrong. I was handling the exceptions pretty uniformly, so I never figured that one out. I had trouble with random access to files. You can, instead of reading files as if they were a stream, you can skip around inside them. And so with my database software, I was making pretty extensive use of random access to files and repositioning and resizing these files while they're open. There were times, and I forget precisely the error, but there was an issue, something like if I positioned the file to the wrong place when I then tried to increase its size, then the resize wouldn't work, or it would act as if it had worked and resize it to something other than what I had requested. It was just mysterious, and I had to just try some ad hoc workarounds, and it was really a pain to debug. I used the include file word to read the cell scripts, and that when you want to debug your cell scripts, you want to insert statements that print strings to standard output. And for some reason, the standard output of included files was being redirected to some, who knows where. I could never figure it out, and that really made the cell scripts hard to debug, made the whole program harder to use. Similarly, I was defining words inside some of my cell scripts, and I had in mind to reclaim this memory by using Gforth's forgetting words. I mean, Gforth has a word called marker, I believe, that helps you do this. And for some reason, I couldn't. I don't know. I couldn't get marker to work in these included files. And finally, there's a word called C, and if you are in an interactive session with Gforth and you type C followed by some word that's been defined, then you'll see the definition of that word. And that worked on Gforth words, but not on, there's some more like primitive words or maybe more optimized words that are defined in assembly language rather than in terms of other Gforth words. And those you could not see, and that was preventing me from debugging certain things as well. So at some point, I read about somebody in a situation like mine, and they had been advised to upgrade to Gforth 0.7.9. This is not listed as an official release of any kind, but there are these, occasional builds. I don't know. They're not daily, I don't think, but so anyway, a later version, and it was not distributed in binaries. I had to build the thing from source, and the fact that you had to build it from source is why I sort of waited so long to even try it. I've just often run into trouble building these projects from source, but I have to say it went pretty smoothly. Maybe there was like one package that I was missing, and I went and installed it, and then I rebuilt Gforth 0.7.9, and it was fine. That seems to have fixed the issue with local variables. In any case, I did considerable amount of development after that and never ran into the problem again. So that seems to have been fixed, and that's pretty major. Marker works in included files, and the standard out from included files goes to the standard out of the calling program, which is what you want. It lets you see those debugging messages that you would insert into your cell scripts. C works on words that are defined in assembly as well as those defined in Gforth. But there is a problem in 0.7.9 I did not encounter before. Sometimes after I shut down Gforth and I'm returned to my Linux terminal, the text on the command line will no longer show up. I mean, it's still there. You can still scroll through your command history, but you can't see the items you're scrolling through. So if you wanted to just repeat the last command, you could hit up and enter, and that would work. But it's hard to scroll through the history and hard to, edit the command line. Hard to enter new commands, and that's kind of a problem. I noticed that the stack reports that occur when you have an error in Gforth are now in this later version 0.7.9 are now colored a different color from the output. Maybe the output is green and the stack trace is red. So I don't know if changing the color of the stack trace or otherwise changing colors of the output caused this problem where after the completion of Gforth, I can no longer see the command prompt in my, the commands at the prompt in my terminal. But that's a problem. And finally, the new version of Gforth it comes with in the Unix directory. It comes with wrappers. I believe they're generated automatically by Swig for Xlib. So some of the pain that I went through of getting Xlib to work through Gforth's foreign function interface is already perhaps taken care of for you. I haven't tried it, but it looks to be the right thing. Of course, most of that pain that I experienced was Xlib itself as designed, so Gforth won't help you with that, but it would give you some head start to have the wrappers generated automatically. So it would be nice to see a new stable version of Gforth, but at the same time, building it from source was easy enough, and it seems to have solved a lot of problems for me. So I would go that way if I were you. That's about it. Thanks for coming by.